Hi everybody, welcome to another video in Calculus 2. We continue chapter 10 where we study about convergence and divergence of a series. Up to this point, what we have are a lot of tests, so let's just review real quick. So the test is the divergent test, only work for divergence. That is the criteria. Next, we have the integral test. When all of these are satisfied, the integral and the series will behave the same. Those are the tests. And there will be the comparison test, direct comparison test, and limit comparison test. So we pretty much will compare a series to another series. So those are all the tests we have up to this point. And then we have the special series. Special series, the first one we have is the geometric series in that form. And then the telescoping series, something like that, telescoping series. And then the P series. P series including the harmonic series. Then we can say it is convergent or divergent. So pretty much right now we have special series, telescoping, geometric, the P series including harmonic series, so 3 special series. And then test, divergent test, integral test, 2 comparison tests, so 4 tests and 3 special series. Now in this section we will have 1.5 tests. The first one is alternating series test, and the second one is kind of a test but only half a test, but we'll see. So up to this point also the comparison test, integral test, all of them only for the positive terms in the series. Now, of course, sometimes we have negative, and we will get to a series where some of them positive, some of them negative. But now we focus on the alternating series. Alternating series meaning that the sign will alternating from positive, negative, positive, negative. Right. So the alternating series converge if 2 things need to happen. The first one, the n terms or the k term go to 0 as k go to infinity. So there's nothing new there. The second one is that the terms in the series have to be non-increasing. Non-increasing meaning that it can be decreasing, could be equal to, could be a constant, but it cannot be increasing. Right, so that's why we write including the equal sign. Right. But most important, what makes it an alternating series is this one. -1 raised to some power. If it is even, it is odd. If it is even, it's positive. If it is odd, it's negative. So when we have -1 raised to some power, so it could be this k plus 1 or k minus 1, doesn't matter. But it will be equal to +1 if k is positive. If k is even, sorry. And if it is -1, it is -1 if k is odd. So in this case, the signs we're alternating between positive and negative. Right. Once we take that away, what's left will be used to determine if this is increasing, if this is non-increasing, and if the term go to 0 as k go to infinity. When both of these satisfy, then the series is convergent. If one of them fails, it is divergent. Right. So here's the first example here. Harmonic series, the P series when p equal to 1 diverges. However, if we throw in the -1 to the k, or k plus 1, k or k plus 1 doesn't really matter. And we have something like this. This one converges because it is decreasing. The bigger the number on the bottom, the smaller the quotient. So this is decreasing. And the term getting smaller and smaller go to 0. So both of this check. So that's why the series converges. Right. So when we look at the problem, we'll isolate the alternating -1 raised to some power. What's left will determine that if it is non-increasing, and if it goes to 0, both of them are satisfied, then it is convergent. Right. Now we have something like this. Now it will be useful if we take the -1 to the k plus 1 in front, and what's left is a sub k. So we're going to take away that alternating sign, and what's left is a sub k. So when we write like this, we say let a sub k be 1 equal to k squared. So ignore the alternating thing. What's left is a sub k. Right. Then we check two things. Does this one goes to 0? Does that is that non-increasing? So even though we have these two, it doesn't matter which one we check first, and I think we'll check the one go to 0. That's usually easier to check. So the first box is limit of a sub k is that equal to 0 as k goes to infinity. So we don't know that yet. So we check. So we check the limit as k goes to infinity of 1 over k squared. Now this one obvious. K go to infinity. Finite divided by infinity. This one equal to 0. So yes, it is. Because this one we have, it goes to 0 because we have 1 over infinity square, which is finite divided by infinity. Yes, so yes, it goes to 0. Second, is a sub k non-increasing? I just say non-increasing. Right. There's a few ways to do that. One, if this is a function, we take derivative. If derivative is negative for every value of k, then it is decreasing. Decreasing is certainly non-increasing. Right. Another way, easier way to do this is a sub k equal to 1 over k squared. The bottom is increasing. The bigger the bottom, the smaller the quotient. So in that case, this is decreasing. So I just write as k increases, one over k squared decreases. And decreases is, of course, is certainly non-increasing. So that box check as well. Right. So both of these are satisfying. The series converges. I'm talking about this one converges. Right, so simple enough. There's just only two criteria that we need to worry about. Right, next, we have this. We don't have a series though. So we should put this in the summation form. So all of that has a fraction form. So why don't we write 2 over 1, 3 over 2, 4 over 3, 5 over 4, and so on. So this is a summation. Right. Summation, we see that the top is 1 more than the bottom. So we could put k plus 1 over k, or k over k minus 1, k minus 1 over k minus 2. It doesn't matter. So we just say k over k plus 1. Let's try to do that. Now, just worry about the magnitude. Sorry. The other way around. The top is bigger than the bottom. So k plus 1 over k. So the top is 1 more than the bottom. K plus 1 over k. Or k over k minus 1. Or k plus 2 over k plus 1. It doesn't matter. Now, next. We just have the numbers. The plus or minus. Worry about that in a minute. Next. The first one is the bottom where k equal to 1. So this series, we start from k equal to 1 to infinity. Right? So that takes care of all the numbers. 2 over 1, 3 over 2 when k equal to 2, 4 over 3 where k equal to 3. Now, the signs, we can say -1. Now, the power here, I can put k, k minus 1, k plus 1, but the first one have to be positive. So, if I put k here, when I put 1 in here, -1 to the first power is negative, so it doesn't work. So to ensure that the first term is positive, we have to make the first term when k equal to 1 to be even. So I could do like I did earlier, plus 1, or just say -1. When we put 1 in here, it is an even number, so the first term is positive. Right, so that's what we have. Now, ignoring this term, ignoring the -1 raised to some power, h of k is equal to k plus 1 over k. So let h of k equal to k plus 1 over k. So h of k does not include the -1 raised to some power. So we don't have that. Then we'll check two things. First one, how about the limit of h of k? Is that equal to 0? So we'll take the limit of h of k, and that equal to limit of k plus 1 over k. Now, we have polynomial, so we'll take the highest power on the top, highest power at the bottom. We have k on the top, k at the bottom, which cancel out is 1. And that equal to 1. And this is not equal to 0. So the end term does not go to 0. So this one fails. We don't need to go any further. And we say this one is divergent. Both of them have to satisfy for the series to be convergent. If one of them fails, it's certainly divergent. So the series diverges. Let's look at another example. Let's just skip that for now. Right. Now we have this. And I said, it doesn't matter the first term is negative or not, it doesn't matter. By the way, it doesn't matter where the index goes. It could go from 2, 3, as long as it is a constant, it is fine. Because after all, adding the first few terms into the series doesn't make the series converge or diverge. It will not change. Missing the first few terms or adding the first few terms to the series does not make it changing from convergent to divergent or from divergent to convergence. If it is convergent, adding a few terms or subtract a few terms, still convergent. Same thing for divergent. Right. Now, by the way, this series has to start from 2 because ln of k, that is 0. I mean, ln of 1 is 0. ln of 0 is undefined. So 0 and 1 does not work where we put in here. We want to have something that is positive or negative, positive or negative. It cannot be 0. So that's why we cannot put 1 in here. Would make it 0. Certainly cannot put 0 in there because ln of 0 is undefined. So yeah. And here we have plus 1 minus 1 doesn't matter. What matter is the negative 1 raised to some power where it's changing from even and odd, positive and negative, positive and negative. So we take this away. So in that case, let a of k be ln of k over k. Now this is a little more complicated, but we still need to check two things. Does that go to 0? Right. So limit as k goes to infinity of a of k, which is ln of k over k. Now put infinity in, we have 0 over 0 indeterminate. So if it is indeterminate, then we will use the Harmonic rule. And well, let's just say this one is infinity over infinity indeterminate. So we will use the Harmonic rule. So taking derivative of the top over derivative of the bottom. Derivative of the top, derivative of ln of k is 1 over k. Derivative of k is 1. So divide by 1 itself. So pretty much we just have limit of k go to infinity of 1 over k. Now the top is finite, the bottom goes to infinity. So this one goes to 0. Because we have finite divided by infinity. Because so yes, this one go to 0. And go to the second one is a of k non-increasing. Now this one is a little more difficult to verify. We can use the ranking though. Certainly that. But another way to do this is just take derivative. So let's say if f of k is that, how about we let f of x be, and correspondingly we let f of x be ln of x over x. If that is the function, when taking derivative, if we can show that the derivative is negative for every values of x greater than 2, then we can say the function is decreasing, and of course certainly the sequence is non-increasing. Of course, decreasing is a stronger statement than non-increasing. Anyway, take derivative of that. Derivative of it, this derivative of this is the quotient rule. So the Harmonic rule is different things. Derivative at the top, derivative at the bottom. So here we use the quotient rule. Just want to write that out. Right, so u prime, the top derivative of ln of x is 1 over x. U prime v minus u v prime over v squared. So that is the quotient rule. Derivative the top, bottom, top, derivative the bottom, and the bottom square. Right. 1 over x times x cancel out, we have 1 minus ln of x over x squared. Now notice that this is for x greater than or equal to 2. Now when x greater than or equal to 2, ln of 2 is that. So this one is positive. Ln of 3 is negative. So what we see is that I will graph the function L1 minus ln of x. Kind of difficult to see, right? Because x squared at the bottom getting bigger, the top is kind of a lot smaller. But I will zoom in and you will see box. Right, zoom out this portion of the graph. Right, so it will be at 2, it will be positive. Right here is positive, but after that it will be negative. So it is C. So in that case, at when x greater than or equal to 3, it will be decreasing. So is that the problem though? And the question, the answer to that is no. Like I said, the whole series, take out the first few terms, they're not affecting it. So in that case, this one is negative if x is greater than 3, greater than or equal to 3, right? So here said ln of 2 is 0.69, what's that? 691, I think. Yeah, 693. Okay. ln of 3 is 1.0986, and ln of 4 is increasing. So why is that important? If this is bigger than 1, 1 minus that is negative. So this is negative if x greater than 3. Because when x greater than 3, ln of x is bigger than 1, 1 minus that is negative. It could be equal to, doesn't matter. And x squared, when greater than or equal to 3, is also positive. So we have negative over positive. It's going to be negative. Now, derivative is negative. That means the function is decreasing. Like I said, missing the first few terms does not affect it. here we can x greater than or equal to 3. Because of that, we say the function and the function and the sequence are associated to each other. So if this one is decreasing, then we say h of k is decreasing for k greater than or equal to 3. So that's the association between the sequence and the series. And because of it is decreasing, then suddenly none increasing. So those two are checked. So the series is convergent. So sometimes it's a little more difficult to determine if the sequence is non-increasing. In that case, we can check derivative. As long as it is negative for some x values greater than some constant, it is fine. We does not have to start from 2. Missing the first few terms does not change anything. So that's why even there's some changing here, still fine. Right, so that is the alternating series test. It's only test for convergence and divergence for alternating series, changing from positive to negative. Right. For alternating series, we can find the remainder as follows. Remainder is what is the difference between the partial sum and the actual sum. S of n is the partial sum. So let R sub n equal to the absolute error between partial sum and the actual sum for the alternating series. And it said the remainder by the sum of this first n terms, then R sub n less than or equal to R sub n plus 1. So we still have the alternating series, but we have to take away the negative 1 to the k plus 1. What's left in the series is h of k. And it says that the remainder is, in terms of magnitude, is less than or equal to the next term. So in other words, the remainder is less than or equal to the magnitude of the first neglect term. So if we go like this, if we stop here, then we say that the R sub n is going to be equal to 1, less than or equal to 1/4, which is the next term. Simple enough, right? So the first term that is not in the partial sum, that is the upper bound for the remainder. The remainder is less than or equal to the next term that is omitted. Right. So let's say we have this series. Now, and let's say we just for 1, we're going to put 1 in, for 2, we put 2 in, then plus minus doesn't matter. If this one continue, and we're going to put n in for k, we're going to have negative 1 to the n plus 1 over n. So this is equal to s of n. Right. This is the very misleading way to do this, so let's not do that. And then alternating. So the s of n is equal to 1 minus 1/2 plus 1/3 minus on the way to the last term is negative 1 to n plus 1 over n. So s of n, we will stop at this term. And it says that approximate the values, how many terms of this series needed to approximate so that the remainder is less than that. So if this is the case, then the remainder is going to be less than or equal to a sub n plus 1. It's always the case. But what is a sub n plus 1? For instance, this sequence, this series I can write as take the negative 1 to the k plus 1 out front. And we write like that. Now ignore the negative 1 to the k plus 1. Of course, this is a sub k. So the a sub k does not include the negative 1 to the k plus 1. So say the remainder is less than or equal to that. So we're just going to put n plus 1 in here. So r sub n less than or equal to 1 over n plus 1. And if we want this to be less than 10 to the negative 4, then we're just going ahead and solve for n. That should be easy, right? The question asks for how many terms. Just go ahead and do that. So 1 over n plus 1 less than 10 to negative 4 is 1 over 10 to the 4th power. Right? Then if we flip it, the inequality will be flipped. So we have n plus 1. We're going to flip it. And then we subtract 1 on both sides. So n is going to be greater than 10 to the 4th minus 1. So that's how many terms we need to have. Is have to be at least 10,000. Of course, we have to choose bigger than 9999. So n have to be at least 10,000. Right? So it is simple enough. So whatever the series, whatever the alternating series, the first term that we omit will give us the upper bound for the error, the remainder. So remainder is less than or equal to the magnitude of the first neglect term. That's what it. So that's what we have. Right. So I did mention that in this section we will have 1.5 more tests to worry about. So this is not really a test, but there's a theorem, very important theorem. Right. Assume that the infinite series converges. The series converges absolutely if there's an absolute value to it. Otherwise, it's said to be converged conditionally. So if we have the absolute values, now the absolute values for the whole thing, for the whole term, then we say absolute convergent, otherwise conditional convergent. So simple enough. And previously we say that alternating harmonic series is conditional convergent, because if we put absolute values into it, it will be a harmonic series which is divergent. So let's write this down. If we have the alternating harmonic series, this one is convergent. If we put an absolute value to it, the negative or positive doesn't matter. Absolute values of that is still 1. And this one is divergent. So we say this is conditionally convergent, because if we put absolute value to it, it will be divergent. So conditionally convergent because it is convergent, but if we put absolute value to it, it will be divergent. Right. Here we have this important theorem and this not very good graph. Right. So theorem, very important. If it is convergent, well, if it is absolute convergent, then it is convergent. So that means absolute convergence implies convergence. That sounds a little better, but it will sound the best when we say if a series is convergent with absolute values, it will be convergent without it. So easy to remember. If it is convergent with an absolute values, it will be convergent without it. And if it is divergent, throw in absolute values, it will be divergent. The note here is that we do not have absolute or conditionally divergent. If it is divergent, it is divergent. No absolute values, nothing. So there is no absolute or conditional divergent. Right. So once again, throw in absolute values. If it is convergent with absolute values, it will be convergent without it. Right. We have 3 examples here to determine if it is diverge, converge absolutely, or converge conditionally. So first thing we do is throw in absolute values, see what happens. So the first one we check is that absolute convergence. So that's the first thing we check, throw in absolute values. Right. So absolute convergence, we will throw in absolute values to it. And when we do that, absolute values of -1 raised to any power, still 1. Right? So there's no positive or negative there. So we just have 1 on the top over square root of k. By the way, square root of k is equal to k to the 1/2. Now, is that convergent or divergent? By the way, this is a P series when P equal to 1/2, right? So we have a P series, P equal to 1/2. And in the P series, if it is greater than 1, convergent, less than or equal to 1, is divergent. So this one divergent, so the answer for this is no. So it is not absolute convergent. How about just convergent? Conditionally. Now if we look at the series, we can write like this. Just write the negative 1 to the k plus 1, and then we have 1 over square root of k. Now ignore the negative 1 to the some power. This is an alternating series, right? So we're going to ignore that and let h of k be that. And we're going to use the alternating series test. Meaning we're going to do two things. First, there's the limit of h of k equal to 0 as k goes to infinity. So k goes to infinity, h of k is that. Of course, square root of infinity is still infinity, so we have 1 over square root of infinity. Of course, that still go to 0, right? Yeah. So if we put in infinity, that's what we have, and that equal to 0. Of course, so if that go to 0, finite over infinity is 0. So yes, the first one check. The second thing we need to check is h of k non-increasing. It's simple enough. In this problem, we don't have to do the derivative. Now, as k increases, square root of k increases, 1 over square root of k decreases. Or we can say as k increasing, square root of k increasing, so 1 over square root of k decreasing. Right? If k getting bigger, square root of k getting bigger, and bigger the denominator, smaller the quotient, so that one decreases. So if it is decreasing, then yes, that box checks as well. So since both of these are satisfied, we check that box. So we say the series converges conditionally, is conditionally convergent. So for this type of problem, the first thing we do is check for the absolute convergent. If it is absolute convergent, then it's certainly convergent, and we don't need to go any further. If both of these are failed, then it will be divergent. Right. We have a few more samples. Sine k over k squared. Notice that we don't have any example like this on the previous section, because for previous section all of those have to be positive. The sine k potentially be negative. For example, when k equal to 2, how about sine 3? Yes, yeah. So for some values of k, sine is negative. So sine 4 is negative. So there's some positive and some negative. But as you see, they do not alternating, right? Positive, positive, and then negative. Sine of 0 is sine of k. sine of 1 is positive, sine of 2, let's just do this. And we go to the table, and you see there's some positive and then some negative, and then some positive and some negative. The sign do not alternating between positive and negative. Right. But regardless, this time they did not ask for that. Ask for, is that convergent absolutely or conditionally convergent, or is that divergent? So first thing we do is check for the absolute convergent. Meaning we're going to put the absolute values into this. For absolute convergent with absolute values. By the way, k squared is positive, so the absolute values actually only need for the sign of k. Right, so how do we do this? By the way, usually I mentioned before that the direct comparison test is not very good, but in this case that's what we have to use. Or the limit comparison test certainly works also. So this is what we do. Because the absolute values of sine could be positive, could be negative, the sine k is, but the absolute values cannot be more than 1. Right? Because sine k is greater than equal to negative 1 and less than equal to 1, we can say the absolute values is less than 1. Then divide by k squared on both sides. K squared for k bigger than 1 is going to be positive. So divide by positive both sides. We do not switch inequality. So we start with that. We have this. Divide by k squared on both sides. K squared is positive. Inequality stays as is. Now, this series is a P series where k equal P equal to 2. So this is convergent. Anything less than convergent is convergent. That is the direct comparison test. So in that case, this is convergent. So convergent with absolute values will be convergent without it. So the original one is convergent because it is convergent absolutely. Right, so we have this now. So when we have that, and then we can add, put the summation in front of it too. So we have that, and we can also write like that too. Let's put 1 to infinity. Now, this is convergent because of the P series where P equal to 2. And anything greater than 1 is convergent for the P series. So, less than convergent is convergent. Greater than divergent is divergent. So this is convergent. Less than convergent is convergent. This is the comparison test or direct comparison test. Now, it is convergent with absolute values. It will be convergent without it. So in this case, we say the series is convergent absolutely. Absolute. Or the series absolutely convergent. Right. Or converge absolutely. That's sure the grammar actually works. So convergent is adjective. Anyway, so absolutely convergent. That's good. Right. Then we don't have to go any further. So that one is convergent without the absolute value. So this is convergent, and this is convergent as well. So we can just put the absolute the parentheses around it. It can be convergent without the absolute values as well. Right. We have the next example here. Do the same thing. Is this one absolutely convergent? So for the series, we're going to put the absolute values into it. So this series, when put 1 in here, we start with the negative terms, which doesn't matter at all. As long as the sign changing, it is alternating series. But like I said, it doesn't matter at all. This one, absolutely convergent. Throw in the absolute values. See what happens. Where we throw in the absolute values, that term is irrelevant because it doesn't matter if it is negative 1 or 1. Absolute values, we turn it to 1. So we just have k over k plus 1. Right? Or you just put the negative absolute values around the negative 1 to the k. Because k is positive, k plus 1 is positive, don't really need the absolute values. That one need the absolute values, would turn into just k over k plus 1. Now, is this one convergent or divergent? And what test should we use? There's a few things we can do. Limit comparison test, direct comparison test, or in this case the easy one is why don't we just take the n term test. So we'll take the limit of that. We use, this is called I call that the n term test or the k term test, but in the book it says divergent test. So we take that term, let k goes to infinity, only the highest power matter. So this is just 1. Now, if the k term does not go to 0, when k go to infinity, the sum will keep changing. We just keep adding some number to it, and some number is not equal to 0, so that will keep changing. Because of that, this is divergence. This is the divergent test. So nope, this is not absolutely convergent. So how about conditionally convergent? That means we don't check the absolute values. So we have this one. We make this alternating series. Alternating series. So in that case, a sub k is equal to, without that alternating term, k over k plus 1. Right, alternating series test. The alternating series test is one of the more popular one because we know for sure if it is an alternating series or not, where we have the negative 1 raised to some power. That changing from even and odd, that is alternating series for sure. So because alternating series is easy to recognize, the alternating series test usually very common to use too. Because if it is alternating series test certainly works. Right, now we check two things. What happened for the k, a sub k as k goes to infinity? Is that equal to 0? Or is the term is non-increasing? Those are the two things we need to check. So actually we don't need to even go to the second one, because when we check the limit of a sub k when k go to infinity, this is equal to 1. Which is not equal to 0. So by alternating series test, this is divergent. So that fail as well. Since both of them fail, the series is divergent. So this one divergent because we use the divergent test. This one is the divergent test. Divergent test. This is alternating series test. Kind of testing the same thing though. Right, so when we ask if a series is absolutely convergent, conditionally convergent, or divergent, this is what we do. First, throw in the absolute values, see what happens. If the absolute values, with the absolute value it is convergent, then we say it is absolutely convergent. Now, if that doesn't work, if with the absolute value it is divergent, now take the absolute values away, is that still convergent? If it is conditionally convergent. If both of them fail, then we say the series is divergent. Right. So in this section, we learned about the alternating series test which consists of checking those two things. Now, at the beginning of the section, I did say that we have 1.5 way to 1.5 tests for the convergent. This is a half of it. So sometimes when we ask if the series is convergent or not, sometimes we just throw in the absolute values. If it is convergent with the absolute values, it will be convergent without it. Or we can say it is convergent in general. Yeah. So sometimes you see this question, they don't ask for conditionally or absolutely, only ask for convergent or divergent. We can even just throw in the absolute values, and then we can just say that if it is convergent or divergent. The reason we throw in the absolute values is because most of the tests we learn up to this point, some only apply for the positive, right? Let me just go back. Right, comparison test, positive terms. Limit comparison test, positive terms. Divergent test, actually this one doesn't matter. Integral test, positive, continuous, and decreasing, right? So, like I said, most of the tests up to this point only apply for the test with positive terms. So, if we want to guarantee that it is positive for a problem like this, throw in the absolute values. If it is convergent with the absolute values, it will be convergent without it. So that one is convergent. Alright, so with that, I stop section 10.6 here. On 10.7, we'll learn 2 more tests for convergence and divergence. But that will be the next section. See you in another video in Calculus 2. Thank you for watching.